Start with some announcements. So as you know, there is a lab out. It's due next week, so make sure you get started on it. Don't wait until the last minute. There's another homework that's going to be out today. Okay, there's a homework that was due last week. I presume you all turned it in. The second homework is actually a hands-on homework, not a written homework. It requires you to go through some of the concepts in virtualization and Docker OS virtualization. So you actually have to do something by downloading some images and trying out virtualization and understanding how it works and so on. Okay? So that's going to be out later today. Keep an eye out for it. It's going to be due next week, okay? A week from today. Lab is due, I believe, a week from this coming Friday. So it's due at the homework is due at the beginning of the week. Lab is due at the end of the week. Okay? So just keep that in mind. Pace yourself well. Very soon there's going to be an exam coming up. We are almost, looks like the semester has just started, but February is going to end this week in March. So March is when we have our exam. Okay? I'll announce the exam dates and so on soon as well. Okay. So let's continue from where we left off last time. So just a quick recap. I was talking about remote procedure calls. RPCs basically allow you to make distributed computation look like centralized computation, and the way you write RPC programs is no different from the way you typically write a centralized program. You take your code, you modularize it by writing functions and procedures. It's just that in a RPC based application, some of the functions are going to be remote, some are going to be local. Okay? When you try to invoke a remote call, you call a function exactly as if you are calling a local function. The underlying runtime takes care of setting up the connection and sending the request and getting back a response and so on. Okay? So that's what RPC is. There were three slides that were left over from last time. I'm going to go through that. Okay? If you remember, I was showing you a sample snippet program that basically was the add RPC. You would make an add call, send two parameters, it would go to the server. Server would sum the arguments and send it back. Okay? So now the question is, since the programmer doesn't actually set up a network connection and so on, how is the RPC runtime system figuring out where is the code for the server? Okay? Which machine does it reside on? What port number does it listen on to, and so on? Okay? So this is referred to as the problem of binding. Okay? So the problem is essentially how does the client locate the server, keeping in mind that it's not the programmer that is actually going to do the network setup and so on. It's the runtime system, but nevertheless you have to tell the runtime system something so that it can figure out where the server resides. Okay. So the way it usually works is you have a naming service that's going to take care of it. So what you will do is the server will export its interface during initialization, which essentially is the set of all remote procedures it's willing to accept from other clients. Okay? And it is going to register itself with a service called a binder. Okay? The binder is essentially a naming service. Okay? Naming services are also referred to as directory services. Okay? So the server registers itself with a naming service of the binder. So when the client makes its first call, it has to first figure out where is the server running. Okay? What machine might it be running, what port number is it running, and so on. Okay? And that requires initialization phase called, you go ask the binder, or you bind to the server, so you ask the binder where is the server running. Okay? So essentially you are going to ask the directory service. The directory service is going to look up whatever services have registered itself with it, and then it's going to send back the necessary information saying here is the server that provides the add service. For example, it's running on this machine and so on. Okay, so you're going to get that handled, and then the runtime system can establish a connection with the server. Okay, so there's a task of finding the server that has to be performed before you can connect to the server and send it remote procedure requests and so on. Okay? It's something you have to keep in mind because there's a little bit of work you have to do in terms of getting the server registered with the service, and the client has to do the lookup. Most of the code is actually written in the stub, but you have to write occasionally, depending on the language, you may have to write something like bind and so on. Okay? So, okay. So that's the binding part. Okay. The other thing to keep in mind is what might happen if there are some sorts of failures, and how do you handle this? When you call a local procedure, okay, you basically do not expect the procedure can throw an exception, which means the parameters were incorrect or something went wrong, so that can of course happen. But often you don't expect the code that the procedure is executing to crash and as the callee is still waiting, because everything is centralized. If the program crashes, everything goes down. Okay, so there is in a centralized scenario. In a distributed application, the client and the server are separate processes. They're running on, perhaps running on different machines. So if something goes wrong, one endpoint may still be running while the other has failed, or the network may have failed. So you have to carefully define what might happen if something fails, okay? So that you can do the necessary things at the client or the server. So here are a set of scenarios of what might go wrong whenever you implement remote procedure calls, and some ideas on how you try to handle it. Okay. So the first one is the client is unable to locate the server. Okay, your client starts up, it invokes an RPC, you will ask the directory service, the service says there is no such server. Okay, so in this case you have to return an error because the server code is not executing anywhere, it hasn't registered itself with the directory service. Okay, that's a very straightforward failure. You cannot locate the server, you're simply going to return an error. Okay. Now some other kinds of errors may involve the client is running, the server is running, the client has sent off an RPC request to the server, but the request got lost on the network or something went wrong from the network's perspective. Okay. So you can have lost request messages. Okay. So these are very easy to handle. Okay. If you could certainly use a timeout mechanism, it says you sent off an RPC request, you have a timeout. If you do not hear back within a timeout interval, you resend the request. Okay. Replies are the same thing. You may have sent the request may reach the server has executed the request and it sent back a reply, but the reply message gets lost. Okay. So you can have a timeout mechanism here again, okay, and you can either retransmit the request or send back a reply. Okay. This might sound very straightforward, but there are many subtleties to take into account here. Okay, the first one is you have to ensure that whenever you retransmit an RPC request, you have to make the operation idempotent. Yeah, I don't know if anyone understand what idempotent is. You don't know what idempotent means? No. Okay, idempotent simply means regardless of how many times you perform an operation, okay, you are going to get the same end result. Okay, so let's take an example here. Okay, let's say you have, let's just assume a very straightforward example. Let's say there's a banking system. Okay, so there is a banking server. Okay, and there's a client. Let's say the client code is running at an ATM or some such thing. Okay. Let's say you deposit some money into the ATM and you essentially you are going to send a request to the server saying you are deposited $10. Okay, so you may say add $10 to the account balance. Okay. So the server is then going to execute this request. Okay. Your bank balance is going to increase and you are going to get back a reply saying you successfully executed this request. Okay, I'm just making up a very simple, somewhat contrived example, but that should give you a sense of what idempotency means. Now let's assume that if the request was lost, you are simply going to time out and send a request again. So that's not a problem, okay, because the request never reached the server. Okay. But however, if the reply was lost, it means that the server actually executed your call. Okay. Only the return direction packet got lost. Okay. Now if you time out at the client side saying I did not hear back from the server and send back your request again, okay, you are going to execute the same call again. Okay. And now you see that the server has stayed here. So if you don't make the operation idempotent, you are going to get incorrect results where you will actually again send a request saying add $10 to the account. Okay. If you execute it twice, you are going to get an incorrect result because you added $10 twice. That's not what you expect. Okay. Idempotency should mean, if you designed a system, and idempotency should say, no, if this is a unique call, no matter how many times you send this call, you should get back the same reply and the state of the server should be the same. Okay, that's what idempotency would mean in this case. Of course, if you have two separate deposits happening, they are two different calls, so they should be treated independently. But if you simply send back the same request to the server has executed it, re-executing it shouldn't cause an incorrect state at the server. Okay? That's an additional subtlety you have to ensure. Okay? The server was stateless, this would not be an issue because there's no information the server tried. In this case, RPCs are operating on stateful servers. Okay, so sending the same request multiple times can cause problems. Is that clear? Now I haven't said how to make it idempotent. That's a more interesting design decision. There are many scenarios there to take into account. I won't go into all of them. Okay, one simple one may be you assign a unique ID to each request. Okay? And you actually keep track at the server what calls have you executed. You may have a window or a buffer. Okay, if the call comes back, you first check saying, did I actually execute this transaction already or this RPC call? Okay? If so, you do not actually re-execute it, but you keep a reply cache saying what was the outcome and you simply resend the reply. And that's one way by which you can prevent, you're explicitly preventing multiple executions of the same call by keeping track of what functions have you executed, what replies did they generate, and then if the request comes back because of network issues, you don't have to re-execute. Okay, so you can use a simple technique like that to ensure idempotent operations. Okay. So those are lost replies. Okay. So it's more subtle than sending, you can't just resegment your RPC system call, or if you do, you have to ensure that you're going to actually have an idempotent system. It's not going to get into problems by re-executing calls. Okay. You could of course change your code so that you, even by re-executing it, you do not get an incorrect reply, but that's more complex. It's not straightforward to do. So that's lost reply. Server failures is another problem. Okay? So in this case, the server code fails. Okay? It can fail during an RPC, it can fail right after the RPC executed, before the reply is sent, and so on. Okay? Now if the server has failed, you will restart the server. But if you do that, you have to also tell the user what might happen if you send a reply request, okay, and you get a reply. What should you assume is the semantics that the server has provided? And there are many different semantics you could provide. You can have what is called at least one semantics, at most one semantics, there's no guarantee you make, or you have exactly one semantics. Okay? At least one semantics says that if you receive a reply from the server executed your call at least once. Okay, perhaps more than once, because there may have been an error. So you restart the server, it looked, it had logged incomplete RPCs, it restarts those and completes them. So your call may have executed more than once. So if you get a reply and your RPC system has at least one semantics, it says that you have actually executed the call at least once. Clearly to get a reply, it has to execute once, but you could have done it more than once to deal with failures. At most one says that if you get a reply, you have executed it at most once. Okay. Exactly one says no matter what has happened, okay, you get a reply, it means that the server executed your call exactly once. Okay. This is what you want. If you send a call, a RPC call, get a reply, you assume that your call executed once. Okay. Not 0, not 2, but once. Okay. But exactly once is hard to achieve, because there can be failures, you have to retransmit packets, you may have to restart the server, re-execute the call, and so on. Okay, so you can have exactly one, but it's more complex to achieve. And you can give no guarantee at all, which means that you send a request, you don't know whether it's going to produce a reply. If it produces a reply, what happened at the server? That's not a good RPC system to write clearly. You want to provide some semantics. Okay? Most of the systems will give you at least one semantics or exactly one semantics. Okay, at least once is easy. You just restart the server, re-execute. So long as you're sending a reply, it's guaranteed you did it at least once. Exactly once is a bit harder. Yes, question.
I'm not clear about how at most once and exactly once would be different from the point of the time.
So the question is, how is at most once and exactly once different from the point of view of the client? The difference will come in some other semantics that I haven't actually talked about. If you're sending a request and you get a reply, okay, at most once will basically mean that since you got a reply, it's executed once, okay, which is what this would also do. But Where they will actually differ is, we will look shortly at what are called asynchronous RPCs or one-way RPCs, where you simply send a request, you do not get a reply at all. Okay. In this case, if you had exactly one semantics, it's guaranteed that if you send a request and the server will actually execute something. At most, one says that it could just drop the request, nothing may happen, because you're not waiting for acknowledgement, you do not know. Okay, in the standard model, they will not be different, but there are other models we haven't even talked about yet. Any other questions here? Okay, so those are failure semantics of the server. You can also have client's failure semantics. Okay. In this case, the client makes an RPC call, and let's assume for whatever reason this is a long-running RPC call. There is no particular threshold on how long the function is going to take before a reply comes back. It may take arbitrary periods of time depending on what computation is encapsulated in the RPC. Okay. And so while the server is executing the RPC, what happens if the client fails? What should be done? Okay. So we looked at what happens when the server fails. Server is restarted, and you try to provide some semantics which allows the client to reason about, if you got a reply, what may have happened at the server from your RPC's perspective. Now what should happen if the server is executing the RPC, the client goes down? Okay. So again, there are several different scenarios. So first of all, we'll call this RPC call an orphan, okay, because there is no one to send the reply to. So it's an orphan computation. But the question is, what do you do with orphan? Okay, so you have to somehow deal with the client failure. There are many different scenarios. Okay, first one is called extermination, where you keep track of client state. Okay, and if you see that the client has gone down, you are going to explicitly kill those orphans. Okay? But this requires you to actually keep checking while the system is running whether the client is up or not. It's not a matter of I received a call, executed it, I sent a reply, and I don't keep track of what has happened to the client in the meantime. So all of these techniques will actually require you to keep track of whether the client is up or not. Okay? So extermination says you are going to maintain disk logs, which will basically not be, won't disappear. They will persist across reboots of the client and the server, and you'll use this to deal with client failures. Okay, we're going to start bottom up. So expiration is a very straightforward technique, where whenever an RPC request comes in, okay, you start executing it, but you give it a timeout value, an expiration time. Okay. If the call is still executing, okay, and your timeout has expired, the expiration time has gone by, okay, you basically check whether the server is up, rather the client is up, and ask the client, should you continue executing it? Okay. The client says, yes, I'm up, I still need a reply, you will give it another expiration time. So let's say you give a 1 minute expiration time to every RPC call. Right? Your call finishes within the 1 minute, there is nothing to do, you send back a reply. If the call continues beyond that 1 minute, you are going to at that point go and check with the client. Say, is the client up? Your call has been running for a whole minute, it hasn't finished. Should you continue? Okay, so you'll explicitly request extensions by periodically checking with clients for long computation. Okay, if the client says yes, continue, you give another expiration time, another minute, okay, and so on. Okay. Very straightforward approach, where you will not have arbitrarily long computations where the client just disappears. Okay, because it may take half an hour for some calls to execute. They may be doing some complex computation. Okay, if the client disappears in the middle, okay, then all of the computation goes to waste. So you are going to keep checking by assigning an expiration time. Okay? And the other two are some similar ideas but implemented slightly differently. There's one called reincarnation, and then there's one called gentle reincarnation. So in this case, you are not going to give expiration time to individual calls, but rather you will just have epochs, which are just time periods. Okay, let's say an epoch is an hour. Right? Independent of when the call comes in, whenever an hour goes by, okay, you will say, okay, here at the end of the hour, there are 10 calls that are still in progress. Okay? And whether to continue them into the next hour, it depends on whether the client is still up or not. Okay? So basically, what that means is you are not going to do a check on a per call basis, but at the end of each interval of arbitrary length that you define, you will see are they executing RPC requests. If so, for each of those requests, are those clients up? And if the clients are up, you will carry those calls into the next epoch. Okay? So what this also says is that point you will find out that the client has failed and you will terminate it. The client will not be present at that point. This just reduces the overhead of keeping track of client failures at epoch boundaries rather than on a per request basis. Okay, that's all it's doing. Okay. In the expiration time, you are essentially tracking each client for every call. When you have notion of epochs, you don't do that. You just periodically check. Okay, so you don't let the calls continue executing for arbitrary periods of time. At the end of each epoch, you are going to say is all the clients that have outstanding RPC is still up and running. Okay, if they are all running, then you continue them. And if some have failed, you terminate those. Okay? So that's reincarnation, and gentle reincarnation is essentially a variant of that where you may actually check whether the client has rebooted and is present under a different port number, for example. If the client reboots and it comes up, it may now have a different port number associated with it. So you can see, ask the client, saying, do you still need this? This was from your previous incarnation, process incarnation. So you will delete only if you cannot find a phone number. Okay? So there are somewhat complex scenarios of how to deal with client failures. Okay? None of them are easy. They require the server to go and track clients. Typically, clients come to servers in the client server. Servers don't go around looking for clients and checking on their state. But in this case, you have to. Here's a slight different way of approaching dealing with failures. Any questions on this? So we'll come back to some of these ideas later on when we have an entire chapter on fault tolerance, which is dealing with all sorts of failures, not just RPC failures. Okay? When we come back to fault tolerance, we'll look at how RPC failures as well as other kinds of failures can be dealt with in many different ways. We'll also look at Paxos as an example of dealing with arbitrary client server failures and so on. Okay, so right now is just a quick look at how to deal with RPC systems and make them fault tolerant. Okay. Now I'm going to talk a little bit about implementation issues, and then we'll switch gears and go on to looking at RMIs and whatnot. Okay, so just thinking about how you go about implementing your RPC runtime. Okay. None of this matters from client programmer or rather application programmer perspective. This is essentially how you write the underlying RPC runtime system. Okay. So first is, many RPC system will give you a choice of what network protocol to use for the underlying communication. Okay. When you compile your RPC code, okay, you can tell the RPC runtime system saying, I want to use TCP, but I want to use UDP as an example. Okay. There may be certain defaults. So if you do not specify something, the system will pick the default choice. But you can also always override the default by specifying what protocol you want to use. Okay. So for example, in early days, RPC systems ran on UDP. Okay. If you know what UDP is, it's a connectionless transport protocol. Okay. Where if you send a network packet and the network packet does not appear at the other end, the network loses it. It is the job of the application to figure out what to do about lost network packets. Okay. As opposed to using TCP. Okay. TCP is a connection-oriented protocol where every packet is acknowledged by the other end, and if packets are lost, you will retransmit them if you do not receive an acknowledgement, for example. Okay. So if you have TCP, you don't need to worry about network packet losses at the application level, because any packet that is sent will eventually be retransmitted and received at the other end. So the abstraction that the network gives you is an error-free channel, okay, lossless channel, because anything you send is going to appear at the other end. It may take an arbitrary amount of time, arbitrary number of tries, but packets will get there. So now, depending on what choice you make, the RPC runtime system will have to deal with whatever happens in the network. So for example, if you say my RPC code is going to run over UDP, okay, it's now the job of the RPC runtime system to figure out, for example, what will happen if a request gets lost, what should happen if a reply gets lost, and so on. But if you use TCP, this wouldn't be an issue at the application level, because the network protocol, the transport protocol is taking care of it for you. So if you send a packet, whether it gets lost or not, it's the job of the transport protocol to retransmit. So you don't have to do anything at the RPC runtime level system. Okay, is that clear? Yeah, fairly important design choices will impact how the system is going to take care of it. Okay, so you can choose your protocol. Okay? Most RPC systems today will run on TCP, so you really don't have to worry about this. But early ones ran on UDP, or you can actually switch yours to run on UDP if you want to optimize connection establishment, overheads and whatnot. Okay, but then you have to deal with network packets that get lost. That's one implementation detail. The other implementation detail is the overheads that are involved in implementing any RPC runtime system, and there are many different overheads. The only one I'm going to talk about here is the network copy overhead, okay, because it's an important one if you have lots of data being sent over your RPC request and lots of data being received. Okay. So what is being shown here is if you actually make an RPC request from a client to the server, okay, and let's say you include an argument, okay, let's say it's an array. You include an array as an argument to your RPC runtime system, RPC call rather. So you have to get all of the data of the array from the client to the server. And how many times is this data going to be copied when it's in transit from the client to the server? Okay. And it will see that actually the number of copies get made for the data to be sent. So it should be clear that there will be at least 2 copies, okay, but there will be many more. Okay, the first, if you only have 2 copies, which is the least, okay, you will actually copy the data from the client process, okay, into the memory of the Ethernet card, and it will get sent. It will appear at the other end. Okay, now when it appears, it will sit in the memory of your NIC, okay, which is the network interface card, and from there you will copy it back into the server process. Okay, 2 copies. Data gets copied from the application to the network card, goes over the network, from the network card at the other end, it gets copied into the server process. Okay. But that is not all what actually is going to happen. There will be many more copies that you will have to perform for this to actually be done. Okay, so here is an example that shows you may copy the data at least 7 times, which if you think about it is a high overhead. If you are sending a lot of data, if you have to make 7 copies. Okay. So here is what might actually happen. Okay. So first you have it in the application. Okay. Application gives the data to the stub. Okay. The stub is going to invoke an RPC call, which is a system call. Okay. So first the application process is handed it to the OS. Okay, that's 1 copy. Because the OS is going to take the data and make a copy of it in the kernel, because it has to deal with that from that point. So the kernel, okay, if you're lucky, you wrote your device driver well, you will hand that memory buffer to the device driver will copy it into the network interface card, and then it will be sent out. Okay, there may be other copies that may happen, but if you write your OS well, you will have another copy there. From there, you are copying it onto the network. To the network, it will appear at the interface card at the other end. That will hand it over to the kernel. The kernel will see which process needs it. It will hand it to the stub. The stub will give it to the server. Okay. So these are all OS level details that you often don't think about. Okay. This is not unique to RPCs. This is true for any socket communication. Okay. You construct a TCP socket or a UDP socket and say send, okay, and you give a buffer to the send. The number of copies that have to be performed for that data to actually go from the sender to the receiver may be at least 7. So the more data you send, the more copying overhead you are going to incur. And as the number of copies increases, this copying overhead can have a performance impact. The reason we actually are even discussing this is there's going to be a performance impact. You include large structs, large arrays in your RPCs, and you have to make many copies for it to get from where it is to where it needs to go, and it's going to impact performance. Okay. So there is a lot of research that has been done to deal with this copying overheads. Okay, if you look at the research literature, you will see an entire area called zero copy architectures. Okay? Or you will see something called zero copy buffers. Okay? Those are all systems that have been written to deal with this network overhead that are incurred in sending and receiving data. And this is true of any network send and receive, and also true in RPCs, because they are using network send and receive. Okay, in this class, we are not going to look at zero copy architectures, but there is an entire area of research where there have been lots of ideas on how to reduce this overhead. The optimal is 2, okay, but that's very hard to hit. And you will have 7, 8 copies happening in most operating systems. So you want to reduce that overhead, improve performance on the network sets. Okay? So I will hopefully try to find a couple of these papers as extra readings if you're interested in, but I won't go into them in the class. Any questions on this? Okay, so the last slide here is a case study before we move on. Okay, so this is a case study on Sun RPC. Okay, this was the very first implementation of RPC systems in a commercial operating system. Okay, so which used to be Solaris. It was in the early days Solaris was called Sun OS. It was designed by Sun Microsystems, which today is Oracle. Okay, so Sun RPC is basically what most Unix-like operating systems use today as well. And it's a very reasonably designed RPC system. A lot of what I showed you last time, which was the RPC Gen compiler and all of that, that came out of this project that implemented the first version of Sun RPC. And let's just look at a little bit of what the system did and how it came about. So Sun RPC was actually designed mostly to implement NFS. If you know anything about Linux or Unix, you'll know that the network file system in Unix or Linux, the de facto one is NFS. Okay? So NFS version 1, when it came out, it was written on top of RPCs. Okay? That essentially meant if you try to read a file, if you say read from your application, that read would go as an RPC request off to the server, because the data file, the file is on the server, it's not on the client. The server would execute the read, send back a reply. If you say write, you do the same thing. If you say file open, any file IO would essentially become RPC calls that go over a network to the file server, because the files are on the server. Okay. So the way they implemented NFS was essentially they built it as an RPC application. Okay, you'll come back and look at NFS when we do distributed file system. At this point, the only thing you really need to know is it's an application that uses RPC. So a distributed file system, okay, that uses RPC. Okay. Early days, RPC systems ran on UDP. Okay? And now you can try to understand why. Okay, NFS was designed to be a file server for local area network. Okay? The client and the server are on the same LAN. Okay? If you are on the same LAN, packet losses are rare on Ethernet. When you're sending a packet over an Ethernet, it may hit some congested routers, and your routers may drop packets and things like that may happen. But if you're sending a packet from a client up to a server that's on the same LAN, same Ethernet, okay, the chances of packet losses go down substantially. Okay. So if you're in an environment where losses are rare, the reason why actually run this over TCP, where every time you make an RPC request, you have to do the connection establishment, send the request, get a reply, tear it up. So there are lots of additional messages get exchanged, as we saw last week. Okay. So they've decided to run it over UDP, and all failures which are rare will be handled by the RPC runtime system by doing this. So retransmits are handled by the runtime system. Okay. Now, today you have a choice. Okay. So they realized soon after they implemented NFS that when you write an RPC application, you can't assume that it will only run over LAN. It could run over a wide area, it could run over the internet. So in that case, UDP is a bad choice for your protocol. It complicates application design. Okay, so they gave a choice to the programmer, saying you decide which protocol you want to use for your RPC application. So when you compile your code, you simply have a flag that you pass with the compiler, and the compiler will take the protocol choice you specify and use that for the stub code that's generated. Okay, that's how it works. Okay, so you have a choice of UDP or TCP. The other thing that they had to do when they wrote this RPC system is you cannot put a limit on how large the RPC request is and how large the reply is. Okay. You will pass a large array as a parameter to your RPC system. So you can't assume that your entire RPC call will be one packet. It could be many packets depending on how many arguments are passed, how large those arguments are. Okay, so you have to write code to take an RPC call. If it exceeds the maximum size of a packet that your network supports, chop it up into packets, send the data, and reassemble the RPC call at the other end, and so on. And same with the reply. Okay. So all of that code is handled by your RPC runtime. You don't need to deal with it. Okay. And as I talked about last time, Sun RPC also defined this notion of XDR, which is an external data representation that allows Sun RPC to work on heterogeneous platforms. You don't have to worry about whether the client is little Indian, the server is big Indian. Everything that you send out is first translated to an external data format, okay, which is universal. So when you receive data, you have to take it from the XDR format and translate it back to your native format. This allows you to deal with various problems, whether you are 32-bit, 64-bit, whether you are little Indian, big Indian, all this is automatically handled because you are always sending data in a known format. It's not going to depend on the sender's native format. Okay. So that was also part of Sun RPC specification, was like XDR representation. Okay. And they basically decided to just go with at least one semantics, which is the simplest thing, meaning that if there are complicated server failures, idempotency is not guaranteed by the system. Okay? Your RPC call may execute multiple times before a reply comes back, okay? And so the application code has to be idempotent. You can't assume that the system will guarantee any idempotency for it because of at least one semantics. So you have to do more work. If you write stateful applications, your RPC call may execute multiple times. If you don't deal with it explicitly, you will have incorrect outputs. Okay, so these are all things the application programmer have to deal with. Okay. That's a quick overview of Sun RPC. If you write any code in C and use RPC system, you are using sort of a derivative of Sun RPC. C, C++ are based on Sun RPC. Java has its own RMI or RPC system, which we'll talk about. Any questions on this? Let's switch gears, talk about other aspects of RPCs. Okay, so let's continue. So having talked about what RPCs are, I'm going to now give you some specialized scenarios where you use slightly different types of RPCs or different semantics for RPCs. Okay. And then we'll talk about how RPCs are dealt with in the Java world, which is really remote methods. Remote methods in the Java world. So first we'll talk a little bit about lightweight RPCs. Okay, so what are lightweight RPCs? So generally when you have an RPC system, it's assumed that the client and the server run on different machines. Okay, so you need to basically take any RPC call, construct a message, send it over a network and process it at the other end. But there may be some simple scenarios where the client and the server run on the same machine. Okay? So the question is, if you have a special case where the client process and the server process are running on the same machine, can you optimize the performance of your RPC system? Okay, the same scenario, ideas would work fine. Okay, you can still construct a message and send it down to the network protocol stack. The protocol stack will say sender and the receiver are the same machine, so no need to send it over the network. It will come back over the protocol stack back to the application. Okay, so you are performing protocol processing even though there is no real reason to send it over the network. The client and the server are on the same machine. Okay. So somehow you want to reduce this overhead for this special case. Okay. And this is where lightweight RPCs come in. Okay. What lightweight RPCs do is they will optimize the overhead of sending and receiving RPCs calls when you have the same machine. I'm going to show a picture here. Let me explain what actually is done first. Okay, so here you are not going to use explicit message passing, but you are simply going to use shared memory. Okay, so an example, I'll draw a picture here. So let's say this is the machine. Okay. This client process. If you did this the regular way, the client would eventually give the RPC call to the server, to the OS, will do protocol processing, it won't go over the network, it will come back here. Okay. But you have paid the price of protocol processing on the machine. Okay. Another way to do this is not do this, but use what is called shared memory. Shared memory is simply a buffer, memory buffer. Wants to make an RPC call, instead of sending a message, it's going to just put the name of the call and the arguments into this buffer. Okay, so you will say execute the add method, here are ing, these are the parameters. So you put it into a buffer and you will signal the server will come and take the arguments from the buffer, execute the code and then send a reply through the buffer. Okay, so you're going to use shared memory as a way to communicate. You're still communicating, except that you use a memory region to perform this communication rather than explicit messages that are going on TCP. Okay. As you can imagine, using a shared buffer where you're simply reading and writing data is going to be much more efficient than constructing a network message and sending it to the OS, performing the system call, doing all the protocol processing, and have that message come to the server, which is a process on the same machine. Okay, this is going to be a lot more efficient to implement. Okay, so this is referred to as lightweight RPCs. Okay. There are several tricks you have to do to make this work. I provided you one example where there are shared buffers. Another example that is actually shown here is you can actually not even have a shared buffer, but just simply push the arguments onto your stack, like you normally call a function, and the kernel will simply make those pages available to the server so that you can just pull it from the stack. Okay. So in this case, you are going to map some of the pages from the client directly into the server address space, which is equivalent to having a shared buffer or a shared memory region. Okay. And then you basically take the data from the mapped pages and write back the results, and the client continues, it has the data available. Okay. In either of these two cases, the thing to keep in mind is you are not going to use explicit message passing to send RPC requests and get back replies. You are using memory as a way to pass information back and forth. Okay. So this is notion of lightweight RPCs are called doors in Solaris. Again, just as Solaris was one of the first OSs to implement this notion of RPCs through Sun RPCs, they are also one of the first OSs to implement lightweight RPC. Okay, they are called doors. Here is an example of a code that basically says you have to declare a door. A door is like a backdoor so that the server process gets access to the pages of the client process whenever an RPC request is made. Okay, so you have to create a door and you have to attach a door. This will make the client and the server communicate with one another through this notion of a shared memory region rather than explicitly calling your regular RPC runtime system. Once you've created the door, the rest of the code is still the same. You simply make an RPC call like you did before. The RPC runtime system will then just stick those arguments into a memory region, and the server has access to that memory region. And just signal the server will come take the request and so on. So this is called lightweight RPCs. Now the nice thing is there are some RPC systems that will allow you to decide whether you are using regular RPC or lightweight RPC at runtime. You don't have to change the code. The code is the same. At runtime you just have a configuration bit that tells the RPC runtime systems and client and the server run on the same machine. Don't use message passing, use shared memory. Okay? Or you will say, go with the default, assume the client and the server run on different machines, use message passing. If you do this, then you don't even need to have this extra code to create doors. You're simply going to write your RPC calls and whatnot. And when you run your code, you're going to tell the system which option to pick. And it will pick one of these two options. Okay, even more flexible than what is done in Solaris. Any questions on lightweight RPCs?
So, this implementation uses message passing or use?
Okay. Question is, does this implementation use message passing? So if you are lightweight RPCs, you do not use message passing. You are using shared memory to communicate. Okay. You are simply going to write whatever information you want into a buffer, okay, and then tell the server to actually go and pick that call and arguments from the buffer, okay, which is not the same as sending a message.
So the door implementation uses shared memory.
Door implementation uses shared memory, and this call is just simply allowing the server process access to a shared memory region. That's all it is. Okay. Any other questions here, please?
Yeah, I mean, so which client or server find out they're on the same version? Who gonna find out?
Okay, who is going to find out whether the client and the server runs on the same machine? So the client and the server or the OS don't find this out automatically. This is up to you when you start the code. When you start the client and when you start the server code, you can pass some configuration bits which tell the runtime system saying, I know that they are running on the same server or same machine, so use lightweight RPC. So it's not that the code is automatically going to find this out. As a programmer, you just write one code, the same standard RPC code. But when you run it, if you know that they are running on the same system, you basically tell it to use the optimized way. That's all. Okay, so it's some human has to tell the system to do it. Any other questions here? Okay, so those are that's lightweight RPCs. Now I'll talk a little bit about some other semantics that RPC systems provide. So until now we have assumed that when you make a call, whether it's a local procedure call or a remote procedure call, it's a blocking call. It's a synchronous call. What that means is the entity that's making the call is going to wait until the call returns with a reply. Okay, so when you make an RPC call, you're just going to block. The call is gone to the server, it will come back with a reply. And then when the reply comes, it will look like the function finished executing and give you a reply back. So that's a blocking RPC. It's also called synchronous RPCs. But those are not the only RPC systems. There are many other semantics you can provide. You can asynchronous RPCs, deferred synchronous, or one-way RPCs. I'm going to show some pictures to explain what they do. Okay, so this is an asynchronous RPC. This figure shows you a traditional synchronous RPC. Okay, this is time. That's the client. That's the server. Black indicates that the entity is executing. Dotted line says the entity is blocked. The client is executing here. It sent off an RPC request, and dotted means is waiting. It's not executing at that point. Request comes to the server. Server executes, sends back a reply. Reply comes here. Client continues execution. Until between these 2 points, it's blocked. Okay, that's what synchronous RPCs will give you. That's traditional RPC model. This is asynchronous. In asynchronous, you are not going to wait for the reply. You're simply going to send off a request to the server and wait for an acknowledgement from the server saying they received the request and continue execution. Okay. If a reply has to come from the server, you will have to be actually interrupted at some later point in time when the reply arrives. Until then, you will continue executing something else. Okay, so that's what is shown here. Okay, this is again time. Here you have the client. Client is executing. It sends a RPC call. Okay. You wait for an acknowledgement. The acknowledgement only tells the client saying the server received your call. Okay. Not that it's executed it or generated a reply, just that it has received it. Okay. So you just wait for an act and then you continue execution. The server is also going to continue executing that RPC call. And what is not shown in this picture, at some later point a reply has to actually go back to the client should the RPC require a reply. And that will interrupt the client and it can then process the reply. Okay, event based, asynchronous way of writing code. Questions, Suresh? Why is the acknowledgement success? So there are many, we'll see that even this will have 3 different variants. We'll wait for the next class to see those. So the acknowledgement is sent simply for the client to know that the packet even reached the server. Okay. If you did not have an acknowledgement, let's say you are running this on UDP. Okay, this is a general principle. No? So if this was running on UDP, what would happen if your request never even reached the server? The ACK at least tells you that the request was received, but it hasn't started executing. Okay? But you are right in that there are some semantics where you will not even wait for this. You simply send off a request and continue execution. That is actually called one-way RPC. Okay? So the client doesn't even wait for an ACK from the server. You simply send off a request and you are done. You will continue execution. Okay? So this will have some reliability issues if you basically run it over protocol like UDP. If you run it over TCP, you send a request, the server is running, the request will get there. You don't have to retransmit. But if you are actually running this over UDP, you have no guarantees at all. whether the request was even going to get there, whether it was executing, etc. Okay? Correct. So we talked about asynchronous, we talked about the bottom one, we didn't talk about deferred synchronous. So deferred synchronous essentially is two asynchronous RPCs. One is the reverse of the other. Okay, so here is the picture that's shown. So you have client at the top, the server at the bottom. Client is executing, sends an RPC request, waits for an ACK, continues. Okay? Server is also continuing, it's executing your called procedure. Now it generated a reply. So the question is, how should the reply be communicated to the client? Okay. In this deferred synchronous RPC, the reply is sent as a reverse RPC. Okay, so here you could just think of an RPC saying, here is your reply, is the call, and then you include the reply in there. Okay, so you basically send back return the results as a reverse RPC, send that, it's also asynchronous, you'll wait for an ACK and continue. Okay. So you have two RPCs, one to make the actual request, the other is actually a dummy RPC where the reply is being sent back to you in the same way from the server to the client. Okay, so this is one way by which the client can actually send back replies when you're asynchronous mode of operation. Is that clear? Any questions on this? Yes.
The replies from which procedure is there identified?
Okay, that's a good question. The question is, if you have multiple calls you have made, okay, you made one call and you continued, made another call, you continued, and so on. When the reply comes back, you need to figure out what is this the reply for. Okay, because the reply is not, so you have to figure that out. So typically a system has to tell you that. It's not that the client will suddenly figure out by looking at the reply that must be the call I made. Okay, so typically the reply will not just have the result, but it will have an ID of the called procedure. So when you send an RPC, you may actually assign an ID to it, or the system may assign an ID to it. So you will know what is the reply you are getting. So this is no different from interrupt processing. If you have sent an interrupt, if there are different interrupts, when you actually get an interrupt, you need to know what it is. This is the same way. When the reply comes back, you have to associate the reply to the call. Okay, and you can use an ID with each call to identify. So in this case, the return value will actually have the ID of the call procedure. Any other questions here? Okay. So that's deferred synchronous RPCs. Okay, so now we'll switch gears a little bit. For the remainder of the class, we'll talk about RPCs in the Java world, which are called remote methods. Okay, or it's called remote method invocations, or RMI. I don't know if any of you have used Java RMIs, but it's the same concept. Okay, you have your Java code is no longer set of objects that reside on one process. Okay, your Java code is distributed across multiple machines. Objects are distributed across multiple machines. You can call a method on an object, but the object itself resides on a different machine. Okay, you know what objects are and methods are if you're not written in Java code. So think of a world where your application is a set of objects. Some objects are on one machine, some objects are on another machine. You may have more than two machines, of course. And you can simply call an object.method. Okay? And depending on whether the object is local or remote, remote may require you to send a message to the object saying execute this method and send back a reply. Okay? This is referred to as the notion of remote method invocation. Okay? So we'll talk a little bit about what RMIs do. One important difference between RPCs and RMI, at least Java RMI, is that RMI support what are called as system-wide object references, which essentially means certain objects can be passed by reference. Okay? In RPC systems, okay, pass by reference is prohibited, it's never allowed because you cannot dereference pointers. Okay? In the Java world, you can pass references to objects. Objects will also be passed by value, as you will see, but you are allowed to pass certain objects by reference. Okay, when you dereference the object, you can actually figure out it's an object on a different machine. Okay, you'll have to pass an object handle that allows proper dereferencing. Okay, that's an important difference. Okay, you can't pass arbitrary pointers. In any case, the notion of pointers doesn't exist in Java. So you can't do arbitrary stuff, but you can pass by reference when you have object references. So we'll look at that as well. So here is a picture that shows you a similar setup as the RPC setup. So you have your client machine here, the server machine here. And both clients and servers, you will have some code which are essentially stubs. But in the Java world, the client stub is called a proxy, the server stub is called a skeleton. Okay, just different terminology, it's exactly the same thing. Your stub is additional code that is generated for you by the RPC, in this case the RMI system, that will actually do the networking for you, sending arguments, receiving replies, unpacking, packing. All of that is going to be done by the stub code. Same is true here, except that the client stub is referred to as a proxy, server stub is referred to as a skeleton. Okay. So the way things, so what is this is also showing is this is your server. Okay. That box there, this square box is actually an object. Okay, object has some state, okay, which may be some variables at the object keys, and then there are methods which are these tiny boxes. Okay, and all those methods can be called from another machine. Okay. So here you have the client is making a call, the call goes over the network, it appears here, you call the relevant method, send back a and as you can see, this is stateful. Objects have state. Okay, those are your private variables. So if your method gets lost and you resend it and maybe the method was actually had executed and the reply got lost, your state may change in an arbitrary way. So you have to deal with all these issues. Okay? So same, just as I said, if you're stateful servers, here by definition many objects are going to have state. So you will have stateful servers. Okay. Now let's look at how some other details. So initially when the client, when the server is written, you have to do two things. Okay. You have to define an interface and you have to define an implementation of the interface. Okay. Interface are the set of methods that you export. Okay, that's the interface, the server. That's the API that the server is exporting. Okay. So you have to distinguish between, this is standard in any object-oriented language. You have what is called an interface to an object and you have the implementation. Implementation is the actual code for the object. Interface simply says these are the set of methods this is object is exposing. Okay, so you basically say this method takes these parameters, this other method takes this other parameter, and so on. That's the interface. So when the client initially binds to the server, okay, it is going to import the interface. Okay, so it's going to load the interface, which is essentially what's called a proxy, into the client address space. Okay, so this tells the client what are the methods that the server exports, and then it can call any of those methods. Okay, and then the proxy is going to actually send the method call over the network to the server. Okay, so there is a concept of loading the interface that the server is actually has defined. Okay. We'll see that there are certain RPC systems where that can be done on the fly without even the client knowing when the code was written what are the functions that are being exported. Okay, so there are some RPC systems where you can just, you don't actually know when you wrote the code what are the methods, you can just have function pointers and simply import the interface. That's not done in Java. In Java you need to know what are the methods and so on. But when at runtime the first thing you will do is import the interface. Then you can call methods on any imported interfaces. So this is basically how the system is going to work. There's another picture somewhere. So I'll come back to that picture. So as I said, the skeleton is the server stub. Yeah, there's different terminology. That's the server stub, that's the client stub. So the proxy is your client stub. Yeah, the proxy's job is to not decide, but figure out where is the server, what endpoint. Endpoint is simply a port number, and what object ID is the server, what objects are in the server, what are their IDs. All of that is tracked by the client stub. It can set up and tear down connection with the server. It is responsible for marshalling and demarshalling of argument, the same thing I mentioned last time. In the Java world, marshalling of an argument is called serialization. Okay? You may have used Java serialize if you've done any Java programming in contexts that are unrelated to RMI. Okay, Java serialize just allows you to take an arbitrary object, write it as a sequence of byte to a file. And when you do deserialize, you can reconstruct the object. Okay? Same idea is true here. When you're passing an arbitrary struct, you serialize the struct, but instead of writing it to a file, you send it over a network. At the other end, you deserialize, and whatever you sent has reappeared. So you are going to use serialization techniques in Java to do the marshalling and demarshalling of arguments. Okay, in the RPC world. Okay, so as I said, you can construct the interface, import the interface when you start off. So that's one. The other thing is binding the client to an object of the server. The object and server here are the same thing. They're actually making calls on the server. So there are two techniques available. One is called implicit binding, the other is called explicit binding. Okay? In implicit binding, you don't actually call any additional functions to bind to the server. You simply go ahead and call the method on the server. And by calling a method on the server or a remote object, your internal runtime system will do the binding for you. Okay? So this is essentially what is shown here. Basically, this is C++ code. So you can see object arrow do something which is an RMI call, and this is going to implicitly bind to the server. So you're calling a method on an object. Object is not local. I need to figure out where it is, so you'll basically go bind it. To figure that out by calling the naming service. Here is a slightly different code where before you call a method on the object, you call bind on the object. So bind is essentially an explicit call to the naming service saying I am about to make a call on this object. It is remote. Go figure out where it resides. What machine is it on? What port will it listen to? Explicit call that you have to write as a programmer. Here that bind is happening implicitly. When you call a method, something internally is going to call the bind for you. Okay, some languages will make you call bind before you can call a method on the object. Some will not. Some will internally call it the first time you call a method. These are just two different philosophies of how to implement runtime systems for RPCs or RMIs. In either case, you have to first figure out bind is whether it's explicit or implicit. We'll figure out where the object resides and then let you call the methods. Okay. So conversely, when the server starts up, the object has to register itself with the binder, so that when somebody calls bind, you can figure out where it resides. So that part also has to happen. Is that clear? Any questions here? So now let's talk a little bit about parameter passing. As I mentioned, in the Java world, this is less restrictive than RPCs. In RPCs, you could only pass arguments or parameters by value. Okay? Passing something by value essentially means you make a copy and send the copy. If you modify the copy at the other end, the original item is not going to change. And that's what passing parameters by value means. Okay, when in the called function, if you change and you pass by value arguments, the original won't change. When you pass by reference, when you change something, the original changes because there's a reference or a connection between the two. Okay. Now, in the Java world, you can actually send some object references, parameters by reference. Typically, if you have a remote object, you will pass it by reference. If you have a local object, the default is to pass by value. Okay, that's a design decision. Why they decided to make that distinction, I don't know, but that's how it works. So here is a picture. It looks a little complicated, but it's not. Okay, so here we have three machines: machine A, machine B, machine C. Okay. Machine B has a remote object O2. Okay. Machine A has a local object O1, and this is where the client code is run. Okay. We'll assume that machine A is making an RMI call to machine C. And in that RMI call, you are going to pass two objects, O1 and O2 as parameters. Okay, so let's say you simply call some method here. Okay, that's a remote method. You pass two arguments. You pass O1, which is a local object. You pass O2, which is a remote object, as parameters. So let's say your RPC call is called food. You are simply going to pass O1, O2 as two arguments. Okay. The default thing in Java is if you do this, since O1 is a local object, you are going to pass it by value. So you'll see there's a copy of O1 that's appeared here because you passed the entire object by value. All of it data, all of its method was sent with the parameter as arguments. Okay, so O1, then you made a copy because you passed by value. But if you have a remote object, you are going to pass it by reference. You're not going to pass it by value. You're simply going to pass a handle, which is essentially a network pointer, to O2 as this argument. Okay, this argument is going to go as a network pointer. This argument to make a copy of O1 and send it. Okay. So on machine C, you have a handle back to O2 as a result. Okay. And O1 is now local. here, meaning you have made a copy. So now if you do any manipulation on O1, this copy original voltage, you're making copies changes here. But if you make any references to O2, will actually go to the original object. Okay. So the important thing is, rather than this distinction, what you need to understand is that you can pass arguments to objects by reference, which is not allowed in RPC systems. So this is essentially requires you to have this notion of a network pointer. A memory pointer typically is a memory address. Okay. Memory address is local to a machine. It's meaningless on some other machine. So if you're passing by reference, you actually need to say this. You have to have a notion of a network pointer which has a machine name and an address on the machine. So when you dereference it, you dereference it on the right machine. Okay. Dereferencing is not local, it's remote. Okay. So that is what you need to implement in order to pass by reference. Which is what Java actually allows you to do. Any questions on this? Okay, so what you should take away is there are more modern RPC RMS systems where you can actually pass arguments by reference. That's the more important takeaway, and it's harder to do. That's also important to keep in mind, because you can't just dereference a memory pointer. You couldn't have passed a pointer. This memory address is meaningless on this machine. You dereference it, you go to that memory address on this local machine. That's not where the object is at. So you have to construct network references or object references that have meaning across the system. Okay, those are called system-wide references. Okay. So any distributed object system like Java RMI will have to make this design decision. Will you restrict parameter passing by value? Will you allow passing by reference? If so, how will you implement dereferencing? What is your notion of a network pointer? All of these things have to be dealt with. Okay, so that was Java RMI. Just to show you some other examples, here is another RMI system. Okay, this is in a middleware platform called DCE. Okay, DCE is an acronym that stands for Distributed Computing Environment. It was a middleware that was built in the late 80s, early 90s, a 20-year-old middleware system. Okay? It doesn't exist anymore. It's outdated and is no longer used anywhere, but it's instructive to understand how they actually came up with this notion of objects and remote methods and so on. So in the DCE world, there was this notion of a distributed object. Objects could be distributed across multiple machines. Client will call methods on objects, and you basically make RMI calls to wherever the method resides. And they actually had this notion of a named object and an anonymous or a private object. Okay. So if you received a call on an anonymous or a private object, you would actually instantiate a new version of that object. Okay. That would be local to only that call, and the call would actually operate on that object's methods and send a reply. This is analogous to a request, a thread per request model, where whenever a call comes in, you start a new thread, it actually executes the request and the thread terminates. Somewhat similar, when a remote call comes in, okay, and it operates on an object, you will create a new copy of the object. Okay. That copy of the object is unique to only that call. So you'll see that there are 3 clients here making a call on the same object. Each of them has been given their own copy. So dynamically instantiated a new copy of the object. You just execute on that object, a method, and then you send back a reply. So that's somewhat different from what we have been seeing so far. What we have been seeing is this, okay? Where when you have a remote object, there's actually one remote object. All methods made on the object actually operate on the same object. The DC world, this was called a named object or a shared object. Okay? The Java world, there are only shared objects. You don't actually have the private notion of a private object. So you have an object, you call a method on it, you will execute a method on that object. Okay, that was actually not the default in the DC world. They actually had a distinction between private objects and shared objects. Private objects were instantiated whenever a new request came in, you created a new, ran the constructor, created a new object called a method. Okay? And the object was then thrown away once the method finished. Okay, these are transient. Those are not transient, they persist, okay, across method calls. So you have these distinctions that other RMI systems make as well. on the lifetime of an object. Is it transient, is it not, and so on. Okay, so very quick couple of slides coming back to Java RMI. That was just an aside to show you other RMI systems. So I'm just going to go through a few slides here so that you get some sense of how Java RMI work should you choose to use it for your lab assignment. So here you have the server. As I said, the server has to define an interface. Okay? Those are the methods for the object that you can call remotely. Okay? And you have to have an implementation. Implementation for each method that you export, you write some code that implements the method. Okay? And then the server program is going to register that object with a remote object registry. This is the naming service. Okay? Remote object registry says, here is an object that I'm willing to accept calls on. This is the name of the object and all those. So you're going to register with the remote object registry. When the client starts up, it's going to look up the server in the remote object registry. That's your naming service. And then once you're bound to it, you import that proxy that I showed you. Okay, so that's the interface. You can then make calls on all the methods that an object has exported. Okay. That's how you would write a standard Java RMI program. Okay, the server has to register itself. Okay, the interface, that is, the interface is registered with the registry. Client looks up the registry, imports the interface, you make calls on the object. Okay. And there are, like I showed you last time, okay, there are similar tools available to you. There's a RMI registry, which is your naming service. But from a programmer standpoint, you have RMIC, which is your RMI compiler. Okay. So you will basically write your interface definition. You will run it through an RMI compiler. It is going to auto-generate the client and the server stub code for you that you are going to then use with your application on the client side and the server side. Exactly what I showed you last time. I ran through the C example where we compiled the code and we saw that it created a set of files that will link to the client side and the server side application. Same is true here. You are going to use this additional tool called RMIC to generate some client and the server stub code. Okay, I'll put up a tutorial on Java RMI on the web page. If you are interested in using it, you'll use these tools as well. And then there are several other things to keep in mind that are going to cause some complications when you use Java RMI. If you had to use synchronization between the client and the server, you have this notion of locks because multiple clients are making calls. You need to lock the shared state before you operate on it. How do you go about implementing locks? Where do clients block? All this has important design implications because if you don't do it right, you will have deadlocks. Okay? Deadlocks is where one entity is waiting on the other is waiting on the first, and no one can make progress. Okay? So when you have this notion of synchronization and distributed code, you are going to run into all sorts of problems. Okay, in a few lectures from now, we will see how to implement a distributed lock. Okay, you've seen perhaps what a lock means in a normal program. Okay, when your distributed application, the lock state itself has to be distributed because whoever is blocking may be a process on one machine is blocked on a process on another machine. Okay. So we haven't seen what a distributed lock is, but nevertheless, you need to think about how synchronization may work. Okay. So first, I think just as a background, you should know that Java supports synchronization as part of the specification. Okay. In Java, if you take any method and you attach the keyword synchronize to it, it becomes a method which has a lock associated with it automatically. You don't actually have to then acquire and release lock. Whenever you call the method, a lock is acquired for you. That's the concept of a monitor. Okay. So if you have, let's say, a function method, let's say that's a Java method for the object. If you say void synchronized, and then you write the code. If you just add this word synchronized to any method, the method gets a lock associated with it. What that also means is that multiple threads try to call this method at the same time, only one thread will succeed. That's the thread that gets the lock. All other threads will block until the first method exits, or first thread exits. Okay. So because Java supports this out of the box, there's a keyword called synchronize. You can turn any method into a monitor or associate a lock with it. Okay, but now when your code is distributed, that causes complications. Okay. So the question is, multiple clients are calling a remote method. You make the remote method synchronized because the method has shared data structures. Then who is going to block and where are you going to block? Okay, so you can actually make the call, have the call come to the server, and then server can block one of the clients and execute the other client calls. Okay, you could certainly do that, but then the problem is what happens if the client crashes while it was blocked. So then the client crashes and holds the lock, then the lock may not be given up, for example. Or you could block at the proxy. Okay, if you feel that the synchronized method is actually has a lock that is in use, you don't even send the RPC. You would block at the client saying, I don't have the lock, so I'm not even going to send my call until I have the lock. Okay. So in this case, you have not even sent the call. You're actually going to be blocked at the client, as opposed to sending the call and having the call blocked at the server. You don't even send the call. Okay. But this would require you to actually implement a distributed lock, so that each client knows whether it has the lock or not. We haven't seen how to do that yet. Okay. This is a better approach because it doesn't need you to deal with client crashes, or it makes the client crashes simpler to handle. Okay. We will look at how to implement distributed lock subsequently, but these are two methods that you can actually use. Okay. Now in the Java case, you actually block at the proxy. Okay. It implements blocking at the proxy so that you do not actually need to deal with some of the subtleties. However, because you do this, applications need to implement the notion of a distributed lock. There are of course libraries in Java that will do it for you, so you don't have to go implement it, but we will actually look at how to implement a distributed lock. Okay. So several things to keep in mind. Okay. So when we talked about RPCs, we didn't really talk about synchronization, but synchronization is going to be important. You have multiple clients making concurrent calls and you're modifying shared state, you will have to implement locks, and then you implement a lock, client crashes, what happens? Is the lock going to be released, and so on. So you have to deal with all of these issues. Okay. So we ran out of time here, so I will continue the next few slides that are remaining here on Wednesday. Okay, so let's stop here for today. Just for those of you who came late, there is a lab that we have put out that's due next week. But the other announcement I made is there is going to be another homework that I'm going to put out today. Okay. This is a hands-on homework that's just going to make you do some very simple exercises in virtualization. Okay, not a written homework, but it will actually make you do some simple exercises.